So in this video, I want to go over the proof for proposition 1.5 on Folland. And if you recall, chapter 1 of Folland textbook is about measure, and of course, before measure, the definitions of sigma algebra was introduced, and right after sigma algebra, the product sigma algebra was introduced. So this proposition is about product sigma algebra, and I'm going to write a claim here. Okay, so let x1 to xn be metric space, and notice that here n is any natural number. So like more importantly, n is a finite. So here we're dealing with countable metric spaces, countably and finite. Okay, and we define the product space X to be equal to the Cartesian product from 1 to n. Let's call it J. J is equal to 1 all the way to n of xj. And notice that because in the proof we need to use the concept of open set, closed set, and those are like how do you define an open set? You need to use metric, right? You need to use this concept of distance. Therefore, we do need to require that X are metric space. So we have at least we have a concept of measure the distance. And therefore we have we have the concept of open closed sets. Okay, so if x1 to xn they are metric spaces and X is a product space, then by convention, or if we don't specify, the metric space equipped on the metric equipped with X is the product metric. And I want to remind you about what the product metric is. So let's write on the gray. If I have x1, xn, and I want to know the distance. I want to measure the distance between those 2 points in my space X. Then I use product metric, and y1, yn, it is defined in the way that a maximum I or j is equals to 1 to n of the distance x1, y1, the distance x n, yn. I think to be consistency, I like to use the distance to represent the difference between, to represent the distance between the 2 points. So here, the metric is the product metric, and here is a metric that equipped with the space x1, capitalized x1, and this is the metric equipped with metric space xn. Okay, and our is if you recall the product metrics, the product sigma algebra 1 to n exi. So here, notice that there's a little bit different. We are not we're not using the sigma algebra generated. Here we're focused more. We're being more specific. So we're not just talking about sigma algebra, where we are focusing on Borel sigma algebra. Okay, and the claim is this one is a subset of Bx. So let's interpret those notations a little bit. Bxi is the Borel sigma algebra of xi. And this notation just means bx1 b bn. Sorry, bx1 bxn. And this is also a Borel set, but Borel sigma algebra, Borel sigma algebra of x, not xi anymore. So xi is each coordinate, and x is the Cartesian product of xi of x1 to xn. So there's a relationship which this could be strict or could be the weaker condition, the weaker one. But we know for sure that if xj's, sorry, let me change this to j. If xj's are separable, then what do we know? Then we know the equality relation, which sometimes would be very useful. So those two are equal. So let me label them 1 and 2, right? Okay, so let's try to prove this. Well, 1 is relatively easy because if we want to show, so on the left is a metric space, right? No, on the left, the sigma algebra, on the right is also sigma algebra. And if we want to show the inclusion of one sigma algebra of the other one, recall lemma 1.1 in Folland, all we need to do is we recognize the generators, and we're making sure that generators of the sigma algebra belongs to the sigma algebra. So therefore, the sigma algebra generated by the corresponding generators is a subset of the sigma algebra. So that's our plan. And let's make an observation. So notice that okay, let's just write it out explicitly. So j is equal to 1 to n bxj is equal to, by definition, pi alpha -1 qj. Sorry, here is not alpha, here's j. Such that uj is in bxj. J is equal to 1 to n, right? Okay, and then so this is the the sigma algebra generated by this set, the definition. And we know that, okay, so this set is our generators, and then each element in the generator looks in this form where u is belongs to bxj, where bxj is from xj. We really want to show, what do we want to show is we want to show this is a subset of this, right? Okay. We so there's another observation, or you can say there's another trick that we need to make a further step. So using theorem 1.1 again, and also notice that bxj is actually a Borel set, right? And the Borel set is generated by the open set of xj. So any so this is a sigma algebra generated. What is the generator of it? The generator is open set. So therefore, using, I think it's proposition 1.4, we can actually write this is equal to the sigma algebra of pi j inverse uj, where uj is no longer in, is of course is still in this Borel sigma algebra, but we can write more explicitly as the generators. Of the Borel sigma algebra. So here, a collection of open sets of xj. So we learned before, or by definition, we know that the Borel sigma algebra is the smallest sigma algebra generated by the open sets. Okay, so now we're good to go. Because since pi j is continuous, and here we're going to prove a little bit why it is continuous. So take epsilon, or not take, but fix epsilon larger than 0. We want to there exists a delta, blah, 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 right? Okay, so the image of pi j is xj1 minus xj2, for example. And we know that naturally this is smaller or equal than, sorry, the distance, I like to use the distance, is smaller or equal than the maximum, right? The distance x, we'll say 1, 1 minus 1, 2, distance n1 minus n2, where so 1 to n. I don't want to use j because I use j to denote the specific pi j. Okay, and notice that the maximum of exactly the product metric. So, and we have therefore x1 1 dot 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 x1 xn1. So those are 2 points in x. This is x1 2 dot dot xn2. So those 2 points, and this is smaller than delta, and at the beginning we can, so this hinted that we should choose delta to be equal to epsilon at the beginning. So therefore it's smaller than delta, and then we're done. So pi j is indeed a continuous function, and because it is continuous and uj belongs to xj, i.e. uj is open set, hence pi j inverse of uj is open. Hence pi j inverse of uj is in Bx. And since all of the generator, every element in the generator of the sigma algebra is in Bx, therefore the sigma algebra is a subset of Bx. And we're done with this first claim. So let me just copy down our conclusion. Yes, okay. And then we're done. And then now, I think the hard part is about claim 2. So claim 2 is like, if we have additional assumption that xj's are separable, then we have the equality between those two sigma algebras. And one very, very important observation is that, so not observation, but lemma, which we proved in previous video. I forgot the exact title for the video, but it is the one about if you have x. So I'm gonna just write down here to make sure that we're on the same page. Okay, so if x is a metric space and x is separable, right? What does it mean by separable? There exists a countable dense subset C in X. And let's okay. And X is separable and denote E to be a collection of balls. So being centered at CI with radius R, where CI is in C, R is in rational. So this is a collection of balls. Then for any open set in X, and let's just give a name. For any open set U in X, right, for any open set U in X, U is a countable union of balls in E, or countable union of elements, countable union of sets in E. Okay, so we proved this in the previous video, and I think the whole proof, once you've seen it, it's hard to forget, and especially after you remember the picture. So the picture gives you very good intuitive idea. So you can review that if you want. So we're gonna just keep going. Okay, so why do we need this? Well, I'm thinking, should I say that first or should I say that last? Okay, let's just make observation, or those are the consequences of this lemma. So I'm just gonna say observation. Observation 1. Okay, so observation 1 is that Bxj is generated by EJ. And we need to prove that it's not super straightforward. Okay. So notice that when we say that a sigma algebra is generated by some set, and we already know the definition for it. So for example, here, we already have a definition for Borel sigma algebra, which is the smallest sigma algebra generated by the open set on Xj, right? And now we're saying we're claiming it is generated by EJ, where EJ consists of this. Sorry, I should define EJ to be. Let's see. EJ is defined to be B C I J R C I J is in C J, R is rational number. Okay. So what are we really, so once you see this, the skill to prove this is really to use the first to make the observation that whether or not each element in one generator can be rewritten in terms of either union or intersection or complement as the element in the other sigma algebra, and they use theorem 1.1. So here, notice that Xj, any open set Xj can be written as countable union of elements in EEJ. Okay, that implies so if we write, so our claim is Bxj is equal to EJ, right? So and let's look at this direction inclusion. So what is the generator for this? The generator for this is open set, and because the generator for this open set, and then in order to show this inclusion, we'd better to show that for every open set we can express in terms as the expressions in here, and yes, we can do that because pick arbitrary. Pick arbitrary open set of xj and xj is equal to the union I is equal to 1 to n as the ball ijr, for example. So sorry, so should be the union I is equal to 1 to n. So it can be written as a countable union of something in the element in terms of this. And we know for sure that since B, C, I, J, R is in EJ, right? Because this is in EJ, so B, C, I, J, R is in EJ, and therefore the countable union JR is in CJ, and therefore what we have is we have this open set. So the generator of Bxj belongs to this sigma algebra. Therefore, Bxj is a subset of EJ. Okay, and for the other inclusion, so what is the generator of this? The generator of this is just the open balls, right? And the open balls are definitely belongs to this because this generator is open set, and of course it contains all of the open set because open balls is because the open balls are open set. Therefore, every element in this every element in the generator, which is EJ, must in this. So let me write it briefly. So EJ subset of Bxj. So MEJ is a subset of Bxj, and then we have yes. So we're done with our observation. So observation 1 is done, and then now let's look at our observation 2. Okay, and I want to emphasize here that in the existence so of CJ is by the assumption XJ is SEPARA separable. And now our second observation is pretty similar to this one, but it's a little bit more involved and you need a little bit more argument. So the second one is Bx is generated by Cartesian product 1 to n Ej. Ej is in Ej. This is a Roman font. Okay. So let's prove this. Still, we're gonna use this lemma. So well, first of all, this lemma works if so X is a metric space. We can check our X is so in the second observation, Ij is equal to 1 to n Xj. It is a metric space because we have product metric. And then this one checked, and X is separable. There exists countable dense subset. This is not directly given to us, so we need to make an argument to show it is indeed true in our case. So let's do that. So recall, we have assumption that recall we have the assumption that each xj is separable. Okay. Okay. That implies there exists a cj, which is countable and dense in xj. Right? Okay. And so our goal, so want to show there exists a C in X that is countable and dense. Okay, and how do we show that? And so consider C is equal to x1, let's use the different letter. So C1, Cn, where Z1 is belong to C1, Cn is belong to Cn. And notice that, of course, this is a subset of X. And notice that those are the CJs, which is countable and dense. So I'm gonna just highlight a little bit Cn, C1 to Cn. And so we argue C is countable and dense in Xj. Okay, how do we show that? Well, recall the definition to show something that is dense, for example. So peak W1, Wn in X and an arbitrary neighborhood of it. And we can call it W, right? Okay, so goal is to show there exists C1 to C. There exists, let me see if there's a better notation. What I want to show is I want to show there exists an element in the element C such that the distance, such that this is inside of the neighborhood W. So I need to denote. Okay, so let's just use Z1 to denote. There exists Z1, Cn in C such that Z1, Cn is in W. Okay. Or yeah, you can use this, or you can use the delta epsilon. They're equivalent. Okay. So how are we gonna show it? Since what? Since W is a neighborhood of W1 to Wn. So since this is a neighborhood of this, we can write W is equal to I don't know, J1 to Jn. So we know that since W1 is in J1 and J1 is open set in X1, so J1 can be written as a countable union. For example, I is equal to 1 to n of the ball centered at Cij with R. R is rational. That means so that means there exists I such that Wi is in BCIJR, right? And then similarly for W2 delta Wn, so our goal eventually is we want to show that right, there exists I such that B is in W1 is in B, Cij, and then now actually this specific I is the Z that we're looking for. And then so we have W1 is in B Z1R Wn is in B ZNR, and you can see that distance between W1, Wn, and C1, Cn is going to be the maximum I is equal to 1 to n distance of W1, C1 distance all the way to the distance of Wn, Cn. Right? And then we eventually want to show this is smaller than so let me think how to say it properly. So it is so if you, for example, this is our xi, x1, and this is j1, and then j1 can be written as a union of the balls or open intervals here, right? And then we have that w1 is in certain point, and that they are super close with one of the point. That is the idea. And now I'm trying to think about how to demonstrate the idea. So okay, eventually we want to show this smaller than epsilon, right? At the beginning, I need to change a little bit at the beginning. So so we pick a point in xi. We want to show so fix epsilon larger than 0. Our goal is to show there exists delta larger than 0 such that for all such that the distance of W1 to Wn minus C1 to Cn smaller than delta implies where this is in C implies that, oh, wait a second. Sorry, I messed up with the definition of the denseness and then the definition for continuity. So overall, what we want is if we pick up a random point in X, we want to make sure that there exists a delta larger than 0 such that, okay, for all epsilon larger than 0, okay, and I'm pretty sure here, there exists Z1 to Zn in C such that the distance between W1 Wn to Z1 Zn is going to be smaller than epsilon. So this is our goal. So if we pick a random point in X and given any arbitrary number epsilon, there exists a point in the set C which we claim to be countable and dense, such that the product metric measurement of the distance of those 2 points is going to be smaller than epsilon. Okay, and then how are we going to prove that? If we pick so W1 to Wn in X, so I am gonna say consider J1 to Jn, where Ji is an interval, okay? Ji is an interval of X. Now G1 is an open set because we cannot say interval because here we're not working on R or anything. So J is an open set. So because Gn is an open set for all I is equal to 1 to n, and notice that And there's an additional requirement. Let ji be the epsilon neighborhood of wi. Okay. So here we're considering epsilon neighborhood of wi for each I is equal to 1 to n. And since ji is open, so there exists, okay. So by previous lemma, ji can be written as union of s is equal to 1 to n of b c s I, comma r, where CSI belongs to CI, where CI is the countable and dense subset of XI, so countable and dense subset of XI. Since this is open by the lemma, it can be written as this. And since WI is in JI, there exists CSI such that WI is in the ball CSIR, and rename. So we're gonna rename CSI to BCI. Hence, so there we find Z1 to Zn such that the distance. Notice that because this relationship, right? This actually implies this r is should be smaller or equal than 2 epsilon, because that's the diameter of the open set ji, and then this bar is completely contained in that, is completely contained in ji. Therefore, this radius must be less than 2 times epsilon. Okay, so we showed hence there exists a point z1 to zn such that the distance between w1 z1 is going to smaller or equal than 2 epsilon, and that implies the distance, if we can using the product metric wn comma z1 to zn is going to be smaller. This is equal to be maximum, and you're comparing what I is equal to 1 to n of the distance wi zi. So this is going to be smaller or equal than 2 epsilon. So my quantifier is a little bit, if you like, I can at the beginning when we define this, we can actually do epsilon over 2 here, and therefore that becomes just epsilon here, and then therefore we obtain the epsilon at the end. Therefore, we indeed, so given arbitrary point and given arbitrary closed interval, we can find a point in C. We find a point in C1 to Zn. Okay, we find this point. Sorry, we find this point in C, which defined to be here. That is arbitrarily close to the point W1 to Wn. Okay, so therefore, hence, we showed what? Hence, we showed that we want to show the denseness, right? Where we are for the denseness. Hence, there exists C. Hence C is dense. And because each Ci, if you look at the definition for C, it must be countable because those are countable. Is dense and countable. Okay. And why do we need this piece? Well, if so now what we are dealing with is we're dealing with X, right? So X is equal to the product space. I is equal to 1 to J is equal to 1 to NXJ. And we have this, and it has a metric space. And we also know that there exists countable and dense subset C of X. So X is separable, okay? And if you define EJ, let me think about, if you define E to be the ball centered at C with radius R, where C is in C, then any neighborhood, any open set of X can be expressed as countable union of sets in E. Okay, so that means if you look at the Bx, which is sigma algebra generated by open sets, and then that open set can be written as a countable union set in E. Therefore, Bx is actually equivalent of the sigma algebra generated by E, right? And furthermore, since BCR is just equal to the product of the balls in R, the product of balls of radius R in XJs. So this is equal to J is equal to 1 to N B C J, comma R. Okay, and therefore Bx is in Bx is in of this. Okay, and where BCJR is in EJ. What is this EJ? This EJ is one that we use. So EJ is, let me write down here. EJ is equal to the ball C IJ R CJ CI is in CI, R is in rational number, where CI is countable and dense subset of countable and dense subset of XJ. So we are almost done. Therefore, we have this. So I think we need to recall something we proved in proposition 1.4. So here in this case, we have x1 to xn, which is countable, right? So I emphasize the countable. Therefore, we can use the second part of proposition 1.4. So recall proposition 1.4. Here, A, which is the index set in that proposition, is countable. It's countable. Hence, Hence, the sigma-algebra generated by the set pi j inverse uj, where uj is in ej is the generator of the sigma-algebra on each coordinate, which is xi to xn. So j is equal to 1 to n. This is equal to the sigma-algebra generated by the Cartesian product j is equal to 1 to n of uj, where uj is in ej, j is equal to 1 to n. That is precisely the definition of the proposition 1.4, and because this is equal to pi j inverse of uj, uj is in bx, j is equal to 1 to n, right? And then this is equal to, as we showed before here, this right? This is bx. And what is this? So by definition, this is equal to j is equal to 1 to n bxj, and therefore we have the equality, and we're done. Sorry, I feel like at some part of my proof I didn't, I became careless on the notations, which may cause some confusions. If you see any typos and mistakes, please let me know. And it is a long proof, but I feel like once you proved it once, you kind of see the pattern, and then it's all about using like translating finding the equivalent sigma algebra, and by using lemma 1.1, and also of making the observation that if your metric space is if your Cartesian product is countable, is by countable or infinite, and there are some useful results that we'll see. We will use those results in chapter 2.